AP in that HTPB to create this composite propellant, the burning rate is going to depend on the particle size. If I have very large particles, what I end up doing is I create these diffusion flames above the surface. Okay, and what that means is a diffusion flame, because the burning rate is depending on the density times the diffusivity, is really the location of it is going to be independent of the pressure. If I have these very small particles of AP in the binder, their length scale is going to be such that when they start decomposing and forming, the monopropellant flame is going to very quickly mix with the fuel, and it's going to look like a premix flame. And if I have a premix flame, that depends on pressure. It's pressure sensitive. So what you typically see then is, as I make very large particles in this mono distribution of adding AP, the burning rate reduces. If I decrease the particle size, then the burning rate goes up. Okay, and you see this sort of trend. So that's why people, formulators, actually mix different size, partly why they mix different size particles, so that they can control the burning rate at different pressures. Okay, so as I said, the last thing I kind of wanted to show you, this is really, you know, in terms of complexity, what people have been starting to look at in terms of trying to model composite propellants. And this really comes about because, obviously, of the advancements in computers. And lately, people have been looking at random packing algorithms to actually simulate what that condensed phase might look like of a composite propellant. So to give you an example here, this is some work that Tom Jackson and John Buckmaster early did, is where they actually developed and used some of, you know, these randomly packing algorithms, and they create then what looks like this as the condensed phase, where they assume they've got three size distribution: a coarse size of AP, a medium particle size of AP, and a fine size. And they just use the algorithm to pack it in some sort of cube. And the regions then that are not, you know, colored is really then where the binder is. Okay, so this allows them, and they validate this. There's actually been some people experimentally that have made certain structures. They know exactly the particle size of these sizes, and then they slice it, and they very tediously start collecting data on what the distributions look like. And you know, you can then compare what the packing models look like compared to these experimental results. Because of the complexity now of the condensed phase in the 3D structure, the computer still cannot handle detailed chemistry. So you got to relax the gas phase chemistry, and you end up working with very simple chemistry. And so global schemes are back introduced. You're moving away again from the detailed mechanisms. That's one of the big questions even in hydrocarbon oxidation chemistry. How do I take a detailed model if I know it where all the knowledge is, and I reduce it to some global mechanism that's still relatively valid over a wide range of conditions? And this just shows an example of a simple chemistry model that's been used in these three-dimensional calculations, where the AP can basically decompose to some decomposed products. The AP can then also react with the binder to form decomposed products in a diffusion flame. And then the HTPB can also react with the decomposed products from the AP to form additional products. And again, it's a crude model, but if you generally get the heat release rate in these three steps, you can do a pretty good job predicting burning rate. So just to show you some of the things that people still deal with, because you're dealing now with a very multi-scale structure, okay, going from the micron scale up to essentially the centimeter scale, and how does this one still deal with those multiple length scales. And so one thing that's been looked at is to basically take the very fine particles and homogenize those with the binder. So you basically make it a pre-mixed system. So here's the original composite propellant that has the three sizes of AP particles: the large, the medium, and the fine. And what one might do then is take the fine particles and just assume that they've been homogenized into a pre-mixed system with the binder, and I end up with something like this. And by doing that, then I reduce the complexity of the calculations. Okay, and this is sort of what you might see then if you do calculations as a function of pressure. This is increasing the pressure from left to right in this homogenized AP composite propellant. And if I look at it, the regions where I have the very fine particles and not the coarse particles. This is sort of this pre-mixed flame that sits off the surface. If I see a large AP crystal, then you can see the presence, there's a monopropellant flame still sitting down here, but now you see the diffusion flame sitting above the surface. As I go to higher and higher pressures, you can see now the pre-mixed sort of flame starts moving closer to the surface because it's pressure dependent. And as I get closer to the large AP crystals, the diffusion flame starts to get longer. And if I go even to higher pressure, the pre-mixed flame moves closer to the surface, and now the diffusion flame's moving further and further away from the surface. So what I see as a function of pressure, it's this pre-mixed flame portion that's really driving the acceleration of the rate. And the diffusion flames here really don't contribute much. All they end up doing is change the topology of the surface, and that one has to deal with. The most recent studies, and I'll end with this, is people are now trying to start to add aluminum particles to these AP composite, and now the aluminum particles become more difficult because they don't decompose the gas at the surface. So now somehow I've got to use the convective flows coming off of the surface with a drag component to lift the aluminum particles into the gas phase, and so that they start to burn above the surface. And that's really the most recent type of studies that have been done. So what I wanted to show you here, since this is really starting to look at how an AP composite propellant burns with aluminum particles, these are some pictures of what it might look like. So this is looking at the surface, and you can see these aluminum particles come to the surface. They can start to melt, sinter, and they come off as agglomerates, and then above the surface they actually ignite and form diffusion flames around the individual particles. And this is exactly what one's trying to model in these calculations. And you can see at the surface here, if you look closely, some carbonaceous material being formed, as well as the AP burying down into the surface. Okay. The other thing I wanted to show you real quickly, remember I said I saved these movies here for the end. I mentioned to you about these high nitrogen compounds, and just to give you an idea, I mentioned some of these high nitrogen compounds don't really form a luminous flame, but they burn very fast. So this is BTAD-C, and if you watch it burn, you can see basically it forms smoke and no luminous zone, but it propagates very fast through it. This is another variation of that called Dado 3.5, and if I do the same thing here, light it, this one actually has sound, and this one over here, not much sound. But again, you can see, the synthesizing these new materials, you can actually use them for different functions. Okay, so I started to talk about the addition of metals to these propellants, and so I want to spend a little bit of time talking about metal combustion. There's been a lot of interest now in metals, again, particularly because of, as I said, going to nanoscale. And, starting out simplicity, why is one interested in adding metals? Well, it's really because of the energy density. So if one looks at the heat of oxidation for different metals, you can look at basically the gravimetric heat of combustion versus the volumetric. And what you find is, the first three metals here are generally the most interesting: aluminum, boron, and beryllium. Beryllium at one time was used, but because it's toxic, no longer used, except maybe in some extreme cases. And the two that are looked at the most are aluminum and boron. Boron has difficulties in its oxidation, and I'll show you that in a second, but it's very difficult to ignite, and the final products sometimes end up not in what you would want thermodynamically, so you don't get all the heat release that you would desire. Aluminum forms a very stable metal oxide, aluminum oxide, that's stable to very high temperatures. It doesn't decompose very easily, and as a consequence of that, you get the heat release you want, and it's relatively exothermic. And so the most common metal that's added to these systems right now is aluminum. There are some systems, as I said, with boron, but they're very difficult to really get in an operational form. So if I look at, one of the questions that one asks about metal combustion is how do they burn? And they can burn in different ways. If I look at combustion of droplets, like a hydrocarbon droplet, I know in the case of a hydrocarbon droplet, the hydrocarbon vaporizes at the surface and it starts diffusing outward. And if I have air in the ambient, the oxygen starts diffusing in, and I get this envelope flame around the droplet. So I have a vapor phase combustion process. But if I have something like a carbon particle that has a very high vaporization temperature, it's not going to have vaporous carbon going outward. I'm not going to have this envelope flame. What I'm going to have now is the oxygen and the ambient coming very close to the surface, and I'm going to have a surface reaction. And whether I have a surface reaction or a vapor phase reaction changes the combustion dynamics, okay? And it changes the ease with which I can get the final products. And so the question might be well, if I look at these different metals, how do they burn, okay? And you can do that very easily by looking at some simple thermodynamics. And in fact, to determine whether it burns in the vapor phase or heterogeneously, knowledge of some of the physical properties and thermodynamic properties about the metal and metal oxide is very useful. For example, if I see that the metal vaporization temperature is lower than that of the metal oxide that it forms, typically it's going to burn in the vapor phase. If I see the opposite, where the solid compound has a higher vaporization temperature than its final product, then I'm going to see it burn as a heterogeneous particle. The other thing that comes out that's kind of interesting is to look at the energetics of the reaction. Okay, how much energy is being released compared to how much energy does it take, for example, to vaporize the final product, to make gas phase species versus final products in the condensed phase. And you can look at that through this simple energy equation here, where Q sub R here is, say, the heat release from the reaction. So how much heat is released from aluminum going to aluminum oxide. Okay, and then I want to get the available energy that's going to be available to decompose that final oxide to make it a gas, because these materials typically are refractory. They form refractory products. And so this term right here is the energy required to raise the temperature of the final product from ambient conditions up to the final temperature, or the volatilization temperature, where it's going to volatilize. So if I take the difference between the heat of reaction and the amount of sensible energy required to raise the product to its volatilization temperature, I get the amount of energy available. If this energy is available is less than sort of the latent heat of vaporization, or the amount of energy required to dissociate the final product, then I'm going to end up with final product in my system in the condensed phase. And what that's going to do then is going to limit the flame temperature, much like a phase change, like boiling of water. Okay, and you can, if you look now at these different metals, and just look at those simple properties. For example, if I look at aluminum here, the boiling point temperature, ambient conditions of aluminum is like 2790 Kelvin. And if I look at the oxide, its sort of decomposition temperature, dissociation temperature is like 4000 Kelvin. So to first order, what this is going to tell me is it's much easier to vaporize the metal than the final product. And so as this starts to react, I'm going to create vaporous aluminum. It's going to diffuse outward. I'm going to have oxygen coming in, and I'm going to have basically a vapor phase combustion process. If I come over here and look at these terms, this term right here is the heat of reaction. Since the heat of formation of aluminum in a standard state is 0, this is the heat of formation of the product, which is the heat of reaction. So this is the energy from the reaction. And if I look at this term over here, this is the enthalpy required to dissociate or vaporize all the metal oxide at the end. And this is the sensible energy required to raise the product from room temperature up to this volatilization temperature. And if I compare this number to this number here, I can determine whether or not the final product is going to be in the condensed phase or in the gas phase. So here, this requires 2550 kilojoules per mole, and I only have available from the heat of reaction this amount of energy. So what it's saying is I don't have enough energy from the reaction to completely dissociate the aluminum oxide. So that factor is going to limit the flame temperature to a temperature of about 4000 Kelvin. Okay, and I can go through all these different metals, and if I look at, for example, boron has a boiling point temperature of about over 4000. Its oxide boiling point temperature is about 2100. So in this case, I'm going to end up having a heterogeneous reaction because I require a lot more energy to vaporize the boron, and in the end that energy is not going to be available. So what's going to happen is I'll vaporize the boron oxide off of the surface, and I'll have a clean surface. The oxygen in the surrounding will come towards the surface and react as a surface reaction, much like a carbon particle. So the aluminum burns like a hydrocarbon droplet, and the boron's going to burn like a carbon particle. If I come over here and I compare this number over here, again, this is the energy required to dissociate the final product and raise it to that boiling point temperature. It has a value of like 640 kilojoules per mole. And if I look at the heat of reaction, it's actually greater than this. So that means the final product is going to be completely dissociated, vaporized. Okay, and the flame temperature won't be limited then by that dissociation temperature. And if you go through these different metals, then you can see the ones that have been shaded are going to burn in the vapor phase, and their flame temperature is going to be limited by the oxide decomposition temperature. And the ones that have been not shaded are going to burn like a carbon particle, heterogeneously at the surface. Okay, and you can go through then and start to categorize how these different metals will react. And you know, you can have these sort of different types of categories. I can have a volatile product, and then underneath that, the metal can be volatile as well. And if that happens, then I have gas phase combustion. If I had a non-volatile metal, but a volatile product, I'm going to have surface combustion. So this is like the boron combustion problem. If I have a non-volatile product, but the metal's volatile, I'm going to have gas phase combustion. This is like the aluminum particle. And if both the product and the metal are non-volatile, what I'm going to have is a surface reaction or even a condensed phase reaction underneath the oxide on the surface. And you can further break this down because some of the final products are soluble in the metal, and that can actually change then the characteristics, whether or not the product is soluble or not, whether or not it forms a coating on the surface. So, you again, recognize that all these metals that we're talking about in particle form and even in bulk form, they have an oxide layer on the surface, right? And that's what basically prevents a very, very small particle from being pyrophoric. Okay, so if I have something like a bulk aluminum and I scratch it, I remove that oxide layer, but very quickly that oxide layer builds up again, and I dissipate all the heat from the reaction in the bulk material, so you don't know of any temperature rise. But if I had a very, very small particle that was maybe on the order of a micron in size, and if I could remove that oxide layer, it would actually become pyrophoric because the reaction at the surface would heat the particle up very, very quickly because there's very little capacity to hold that energy, and it would become pyrophoric. Okay, so let me kind of show you, based on what I just talked about, how the mechanisms can also change. So this is a plot of flame temperatures that were calculated just from thermodynamics. So something like, using the NASA chemical equilibrium analysis code versus pressure. And for example, let's take a look at 1 atmosphere here. This solid line right here is the vaporization temperature of aluminum as a function of pressure. So it goes up with pressure. And if I look then, the other lines then are the equilibrium calculations for different types of mixtures. So if I look at this long dashed line right here, this is the equivalent of aluminum burning in air, and its flame temperature would be about 3,600 Kelvin. If it burns in pure oxygen, it's close to 4,000 Kelvin, the volatile temperature of the final oxide. And so what this tells me then, if it's burning in air, the flame temperature is higher than the boiling point temperature. So what happens is I have this detached flame, and the heat from the envelope flame diffuses back to the surface. It vaporizes the aluminum diffuses out to the envelope flame, meets the oxygen, and reacts to create the high temperature. And the same thing happens to these others. But notice what happens is if I go to very high pressures. Eventually I find a situation where the boiling point temperature rises quicker than the flame temperature. So at these very high pressures now, if I look at this, the boiling point temperature ends up being higher than the flame temperature. So no longer can I have this envelope flame sitting off the surface, coming back and providing heat to the surface to vaporize it. So now this flame has actually changed from a vapor phase flame into a heterogeneous type reaction, much like the carbon particle. So suppose I wanted to react the aluminum in liquid water. Okay, I wanted to look at underwater propulsion and use the liquid water as my oxidizer. Okay, or in a nuclear accident where I have a lot of water around with aluminum. Well, what you see in this case here is this is the flame temperature of the aluminum liquid water reaction, and if I follow the boiling point, it has a crossover at a much lower pressure, near 1 atmosphere. So in this case, if the aluminum is burning with liquid water, it's going to almost look more like a heterogeneous reaction than a vapor phase reaction. And you can do this for CO2 and these other compounds to see where this transition might occur then. Okay, so to show that experimentally, here's some experiments that were conducted by making single aluminum particles about 200 micron in diameter, and in air and in water and pressure effects. So let me kind of show you. This is a single particle that was ignited with a laser in like a drop tower. And so the particle's ignited, then it flows drops at a very low Reynolds number and Grashof number. And as a consequence of that, buoyancy effects are not that important. And what you're seeing here then are the strobed images of that particle burning. And in the center here is the parent particle, and then you'll see a dark zone. And the dark zone is where the aluminum is diffusing outward, the oxygen in the air is diffusing inward, and then you see the flame, the circular spherical flame sitting off the surface. This is where the aluminum is reacting with the oxygen to form the final product, aluminum oxide, okay, which is in the condensed phase, and it's because of its emissivity is radiating. Okay. Now if I switch it and I change the oxidizer to steam, what you see then is I no longer have this detached flame, and the flame sits very close to the surface, and these bright spots here are basically lobes of aluminum oxide gathering on the surface. The emissivity of aluminum oxide is much different than the aluminum, so it looks much brighter even though it might be at the same temperature. And as the lobes gather, you have a different surface temperature between the aluminum and the aluminum oxide. They gather into these lobes and eventually they fly off. So you can see the combustion type of process actually changing depending on oxidizer. Also, if you look at what's happening now and going from 1 atmosphere to 2 atmospheres, to 60 atmospheres in air, you can see now the flame coming closer to the surface, and eventually the flame sits down on the surface if I got the high enough pressure and I change that vapor phase combustion process into a heterogeneous process. Notice also, as this particle is burning, I can have 2 different size distributions of aluminum oxide being formed. The first size distribution is going to be related to the size of the parent particle, because there's always going to be a little bit of aluminum oxide that comes and gathers on the surface. And when it's flowing, you'll see there's recirculation zones. If the particle is actually moving, you actually get recirculation zones of vortex, and it can gather a lobe on the surface and accumulate aluminum oxide. So one size distribution is going to be related to the original particle size, and the second size is going to be related to the size of the particles out here in the flame zone. And they come about by a nucleation process. So they begin out at the nanometer primary size, and they aggregate up to maybe a couple microns in size. So you end up with this bimodal distribution of aluminum oxide. I mentioned about this limiting flame temperature characteristic, and you can also see that in these thermodynamic calculations. These are just CEA calculations where what I'm doing is I'm either taking enthalpy out of the calculation or I'm adding enthalpy. If I take enthalpy out of the initial reactants, it's like a heat loss during a combustion process. If I add enthalpy, it's like adding heat during the combustion process. And what you see then, 0 here, is the case of where you'd have the standard conditions, heats of formation for the oxygen and the aluminum. If I go to a negative value, that means I'm taking enthalpy out and there's a heat loss process. But look what happens. So this is burning in oxygen. The flame temperature is about 4,000 Kelvin. As I take the enthalpy out, you can see the amount of gas phase species start decreasing, the amount of aluminum oxide increases until I get to a temperature where all of the gas phase species disappear and I'm left only with aluminum oxide. Okay? And then the temperature starts to fall. If I start adding enthalpy to the system, again, the temperature doesn't change. I continue to dissociate more and more of my aluminum oxide. I make more gas phase species until all the aluminum oxide has been dissociated and all I have is gas phase species, and now the temperature starts to rise. So what this is effectively showing me is sort of the equivalent of the latent heat of vaporization of aluminum oxide in this system. Okay, and what it does is it creates what's like a limiting flame temperature. So if I'm burning aluminum particles and it has a little bit of heat loss, the temperature is not necessarily going to drop, because it has this enthalpy change to overcome before, you know, I either condense all the gas phase species convert back to aluminum oxide, and the temperature can eventually start to fall. Okay, so we've actually gone in and measured around single particles what the distribution of the flame characters might look like in these falling droplets. And what I show here using laser-induced fluorescence are some of the intermediates in the flame temperature that surrounds these individual particles. So this is a particle, again, that's about 200 micron in diameter. This is the dark zone. This is the flame zone sitting around it in a spherical zone. What you're looking at here is essentially the fluorescence from aluminum monoxide. This is the small suboxide that's formed after the aluminum gets vaporized. So if I were to look at the reaction process, first I'd form the aluminum would be vaporized. That would be then converted to aluminum monoxide. That would go through maybe Al2O in more and more steps, eventually to form Al2O3, the final product, which would be a condensed phase product. And so as a function of non-dimensional particle radius here, you can see the aluminum monoxide grows off the surface, it then falls off, it's oxidized further, eventually forming Al2O3. And if you look at the temperature measurements, which are obtained from basically the ALO measurements, looking at two different wavelengths, you see that the temperature remains nearly constant, so this limiting temperature range over a very broad radial regime, indicating its limited temperature regime. The way in these calculations or in experiments that the aluminum oxide concentration was obtained was by having the particle fall, and as it falls, its burn process is interrupted by a silicon wafer. So I have this three-dimensional structure coming down, it collapses onto a silicon wafer, and it's quenched. Okay, and that's what you're seeing over here. This is the parent particle, and all the smoke in the ring basically quenched out on the silicon wafer. And what you could do then is electron probe microanalysis from the particle radius outward to get the relative amounts of aluminum atoms and oxygen atoms to basically back out what this distribution of aluminum oxide looks like. What you find very near the surface, if this is burning in air, you actually find aluminum nitrides because it's very fuel rich in this region, and you can actually form aluminum nitrides in the region as well. Okay, much like classical droplet burning behavior, if it's a diffusion controlled process, what experiments tell me as well as simple theory is I can predict the burning rate through what's referred to as a d-squared law. This basically says that the diameter of the particle at any future time is related to the initial diameter squared minus a burning rate coefficient times time. Okay, and what people do then is they try to measure these burning rate coefficients for different metals, different droplets, so that they can use it in calculations. Indeed, what you find, if you do that as a function of pressure, as you might expect, because it's a diffusion flame, there's very little dependence on pressure, and the burning rate constant remains nearly constant as a function of pressure. Okay, so I mentioned, the fact that I could have a heterogeneous process, I could have a vapor phase process, but I can also have different modes of combustion. I can, in some cases, I can have a diffusion flame envelope sitting off the surface, but in other cases, depending on the size of the particle and the environmental conditions, instead of this process being diffusion controlled, it could be kinetically controlled by a surface reaction. And so I showed three different types of burning cases here. The two on the left are basically diffusion controlled. The first is the case that I've been talking about, very similar to droplet combustion, what I mentioned for the aluminum combustion that we just saw. I have the aluminum fuel, for example, being vaporized, the oxidizer coming in, reacts in what looks like nearly a flame sheet, and the temperature goes up as to the flame temperature. The heat feedback to the surface continues to vaporize it, and I've got this feedback system. Well, I can also have a situation where the reaction occurs on the surface, much like a carbon particle, but it's still diffusion controlled, and I would have profiles like this as well, where now there's very little fuel on the surface, the oxidizer goes away because this is really the reaction, all the products are formed on the surface, and the maximum temperature is on the surface, but this process of getting oxidizer to the surface is diffusion controlled. If the particle gets very small, what I can end up seeing is that eventually this type of reaction becomes kinetically controlled. Okay, where now the diffusion process of getting oxidizer to the surface is very fast, but the limiting process is the surface reaction, the rates of the kinetic step on the surface. So I can differentiate between what's referred to as a kinetically controlled reaction versus diffusion controlled reactions. And if you develop the simple theories, just solve the energy equation and the simple species equation, say for a one-step reaction, you can end up calculating the burn times for each of these cases. And that's what I've done in this slide here without going through the mathematics. And what you find then is if I have a diffusion controlled process where I either have vaporization of the fuel in an envelope flame, or I have a surface reaction but it's totally diffusion controlled, I see that the burning time is proportional to the quantities on the right. And the thing I want you to note, and many of you may have seen from hydrocarbon oxidation, if it's diffusion controlled, then the burn time is dependent on the initial droplet size squared. It has a d-squared dependence, much like I showed you from that empirical law. Okay, and the driving force, the B here, is referred to as the the Spalding number, and depends on basically the amount of mass fraction of fuel at the surface, the amount of mass fraction of oxidizer far from the surface. And so that's what this is showing here. I here is the stoichiometric coefficient, the mass of fuel versus the mass of oxidizer required for a stoichiometric reaction. This is the mass fraction of oxidizer at infinity. This is the density of the gas, the diffusivity in the gas. This is the density of the particle, and obviously the particle squared. If I get into a regime now where this is a kinetically controlled process, and now I have a surface reaction with a rate constant, I end up getting basically a burn time that has a functional form like this. So in this case, you can see now, instead of being proportional to the diameter squared, the burn time is proportional to the diameter. And K here is the rate constant for the surface reaction, which is going to be temperature sensitive, and also now it's pressure sensitive as well, because that's going to also affect the rate of reaction at the surface. If I look at these two conditions, and formulate what looks like a Damcaller number, which is the ratio of, say, the characteristic time for the diffusion burning versus the characteristic time for a kinetic burning, and take the ratio, and I set the Damcaller to 1, that sort of defines the regimes that are going to be diffusion controlled versus kinetically controlled. Okay, and so I can look at this and just symbolically say, well, what's going to make it a diffusion controlled process versus a kinetically controlled process? Well, you can see here, if the original diameter is very small, then the limiting time is going to be the kinetic time is going to be basically kinetically controlled. If I lower the temperature, if the temperature in the ambient's low, or if the reaction temperature is low, that lowers K here. That's also going to lead to a kinetically controlled process. If I lower the pressure, it's also going to favor basically a kinetically controlled process. So if I have a high pressure, a large particle diameter, it'll be diffusion controlled. And indeed, if you conduct experiments, this is for the combustion of boron particles, what you find then is, say, at atmospheric pressure here, if I'm at very large particle diameters, I get a dependency that looks like d squared. And then as I get to about a little below 100 micrometer in diameter, I start getting a d to the first law. If I raise the pressure to 35 atmospheres, then what's predicted is the diffusion controlled process is continued down to lower diameters, and then eventually again it becomes kinetically controlled. Okay, and I can do the same thing. I can look at different particles. I can also look at aluminum, for example, and generate a plot that looks like this as well. So here's the burning time as a function of diameter for aluminum burning in oxygen. For large particles, you find it empirically, it depends on d to the 1.8, not d to the 2. This has been sort of hypothesized due to the fact that in the case of aluminum versus boron, I'm always going to have a little bit of oxide remaining on the surface. It's going to create a lobe, and what it does is it partially covers the surface, and it affects the available surface area for vaporization, and so that lowers essentially the d squared law to this. And if I go to smaller diameters, again I see a slope change here, and I notice that the reaction rate is now dependent on the ambient temperature, so I'm affecting the reaction rate at the surface. The lower the temperature in the system, the slower the reaction rate, the longer the burning time. So that tells me it's a kinetically controlled process. What I also find is ignition temperatures are affected by the particle size. And in the case of aluminum, very large particles, the ignition temperature is related to the temperature at which I start to melt the aluminum oxide. So that's about 2300 Kelvin. But if I get this very small diameters, what I see is the ignition temperature starts to drop, and it becomes closer to the temperature at which the aluminum melts, which is about 900 Kelvin or a little bit higher. And so, again, you can vary the ignition temperature depending on the particle size. Okay, so what I'm sort of extending here is I'm starting to go down to the micron and into the nanometer size. And the question that I addressed early on was what happens as I shrink the particle size in terms of combustion. Obviously, I just showed you that what I would expect is the burn time would change from a diffusion controlled process to a kinetically controlled process. Okay, but what are some of the other features that if I can shrink the particle, I might see in the system? Well, if I get very small, what happens is, and I look at basically a nanoparticle, more and more of the atoms in the particle lie on the surface, okay, and less in the bulk. And the atoms on the surface have a lower coordination. That means they have free dangling bonds. Okay, and so their bond energies and energetics are different than those in the bulk. Okay, and as I shrink the particle, what it looks like is that the particle thermochemical characteristics as well as its physical characteristics start looking more like the surface atoms than the bulk atoms. And so here's an example of that for looking at spherical iron crystals. As I start to shrink the particle size, you can see the number of surface atoms starts to increase and the number of bulk atoms starts to decrease. So in around 10 nanometers in diameter, I should expect significant changes in some of the thermal characteristics and physical properties. And indeed, if you look at, say, the melting point or the heat of fusion for tin particles, that's what you see. So as I start to shrink the diameter, you can see in this plot right here, the melting temperature starts to fall off, and the heat of fusion also starts to fall off at a slightly larger diameter. Now this is important because, as I just showed you, ignition temperatures of aluminum particles are going to be related to melting conditions. Okay, if I can lower the conditions at which either the metal or the metal oxide starts to melt, I can lower the ignition temperature, and that's what I showed you happened in some of those experiments. Okay, so what are some of the additional characteristics of nanoparticles? Well, as I shrink the particle down, I increase the specific surface area. That leads to an increased reactivity. It also increases the catalytic activity. The classic example there is if I take gold particles. If I am looking at a micron gold particle, it has no catalytic characteristic at all. If I shrink it to the nanometer, it's actually a very good catalyst. I also change the melting temperatures of both the metal and the metal oxide. I can affect the vaporization temperatures as well. I lower the sintering temperature. This may not be a positive effect, and there's other effects that can be introduced as well. But not everything is great by going to the nanometer scale, and one of the negative characteristics is shown here. Okay, as I mentioned, all metal particles have a naturally occurring oxide layer on the surface, and that's what prevents them from becoming pyrophoric. And typically that layer could be anywhere from a few nanometers thick to tens of nanometers thick. And what you generally find is, as I shrink the particle, the thickness of that layer doesn't change. Okay? And so what that means, as the particle gets smaller and smaller, I'm not changing the amount of oxide on the surface, but I'm decreasing the amount of metal in the core. So if I'm looking at this from an energy content point of view, as I shrink the particle, I'm really carrying more dead weight with me, and I'm losing the energy density of the particle. And that shows up here, for example, looking at changing the particle size and the percent energy content for a 2 nanometer oxide layer or a 3 nanometer oxide layer. And what you can see here, if I look at a particular dimension down here, if I get to about maybe 50 nanometers, you can see that I've lost 40% of the energy content. So eventually, if I were to shrink this particle down to 10 nanometers, it's almost going to be all oxide. There's not going to be any metal content at all. So one of the important issues to start thinking about is, how can I passivate the layer of aluminum without the naturally occurring oxide with something else that's energetic? Okay, and that's one of the research topics that people have been looking at. So to give you a little bit of brief history then on how nanoparticles have been added and looked at from an energetic point of view. The first thing was, in the 1990s, people recognized they could start fabricating nano metal particles. And this partly came about from the fact that transmission electron microscopes were coming available, scanning electron microscopes were coming available, and people could actually see information at the scale. And as a consequence, people started to fabricate nano aluminum particles, nano boron particles. And the interest was then at that stage, well, suppose I just take the micron particles out of a composite propellant and I substitute them for a nanoparticle. What changes in terms of the combustion behavior? And indeed, what people saw was the burning rate increased, but it didn't increase as much as they actually thought it would have. And part of that came about was from what I just showed you in the previous view graph. I'm losing energy content and what happens with regards to how the particles accumulate at the surface. But what I show here in the top graph, people have made nano aluminum. They've also made nano oxidizer particles. So this is nano RDX, and they've done this through a supercritical processing process where they take the RDX, they dissolve it in a supercritical fluid, expand it through a nozzle, and basically let the solvent come out at maybe CO2, and the particles start to nucleate, and you control the nucleation process to restrict the size of the particle. As I mentioned then, it was early recognized that, the oxide layer is a negative feature. And so the question was, can I passivate these small particles with something other than the oxide layer? And so here's a couple of examples where researchers have looked at different passivation materials. In this case here, palmitic acid or oleic acid on aluminum particles and iron particles. And to give you, this person on the right who coated the iron particles with oleic acid, here's one of their interests for doing that. And this goes to really an air-breathing combustion problem, more so than a rocket problem. In a gas turbine, in future gas turbines, what you're going to end up finding is the fuel lines are supercritical. And as you get very close to the fuel injector, the temperature increases. Okay? And what's typical of a fuel in a gas turbine is there's always a little bit absorbed oxygen. Okay? And as the fuel goes through this, as the temperature rises and I get into these supercritical conditions, just before it's injected, people are finding I'm forming carbon deposits, and that's starting to clog the fuel lines and injectors. So the question is, how can I minimize that carbon deposit process? So he thought, well, if I take these coated nanoparticles of iron and I add very small quantities to my fuel, and I can control basically the temperature at which the ligand, this oleic acid, comes off of the iron particle. Suppose that comes off at a temperature just below the temperature at which I start to make the carbon deposit. What I'll end up doing is then the oxygen in the fuel line will preferentially react with the iron particle versus the fuel, and I'll minimize the amount of carbon being formed. Okay, so it's a different way, looking at how these particles can actually be used. What I show in the bottom here is even more interesting. This is a situation, suppose now I have an aluminum particle, and I get rid of the oxide on the surface, and I use a hydrocarbon ligand or something, and I bond it to the surface, so it passivates the surface. Okay, now, this hydrocarbon ligand is basically like a CH compound. And now suppose, so at the head end, I'm bonded to the aluminum, and that passivates the aluminum. And at the tail end, suppose now I take one of the hydrogen atoms off, and I functionalize it with something like an NO2 group. So now, all within this nanoscale structure, I have my fuel, which is the aluminum, I have my binder, which is this hydrocarbon ligand, and I have my oxidizer, which is the NO2 groups tailed at the end. And I can use that as a building block to start building composite materials. So it's really like a bottom-up approach to start building energetic materials. And the example shown here is a case where the aluminum was actually passivated with a fluorocarbon. Okay, in this case, the fluorine acts as the oxidizer. It's very reactive with the aluminum, and it makes basically aluminum fluoride. And so the passivation layer is the oxide, and the aluminum is the fuel. And another example over here where a cryogen technique was to use Cl20 and nitrocellulose. So the idea of starting to fabricate energetic materials at this very small scale. There's another important length scale as I start to shrink the particles down to the nanometer scale. Okay, and that's the scale where I start looking at the dimension of the particle relative to the spacing of the molecules, the mean free path. And when the particle gets so small that it's of the size of the mean free path, the question comes about, am I still in a continuum limit? Can I distinguish the particles from the molecules? Okay, and when that happens, I move into a free molecular regime. And what that means is I start to change the dynamics of particularly in terms of models, how energy is transferred and species move between the particle and the surrounding gas. Okay, and that's usually defined through a Knudsen number here, which is the mean free path divided by the radius of the particle. The mean free path, if I use kinetic theory, can be defined as shown in this equation down here, and you can see it's inversely proportional to the pressure of the system. And if I look at the temperature of the system, it's proportional to the temperature to the half. Okay, so if you go through and look at a 100 nanometer particle, for example, and I assume I'm at atmospheric pressure, and I look at the typical temperature range that would be encumbered in a combustion process, ambient up to say 3,000 Kelvin, a 100 nanometer particle is always in the non-continuum regime and below her. Okay, so there's a transition regime around Newton number of 1. And what this means then, if I'm in that transition regime, what comes about is the question is how is the energy transport between the particle and the surrounding gas affected? And what it leads to is what's referred to as essentially a slip or jump condition. Okay, and what that means is at the surface, the temperature actually will jump as well as the concentrations. And that affects then basically the energy and momentum exchange between the particle and the surroundings. Okay, so I may not have an efficient process. You know, if I have a conduction process, when a molecule hits the surface, I typically assume in the continuum limit, it's going to assume the surface temperature when it goes away. But here, if at the non-continuum limit, when it hits the surface, that energy exchange process is not going to be that efficient anymore. And when it moves away, it may be at a much different temperature, much lower. So that efficiency of exchange of energy may be very inefficient. And so that's typically done theoretically by introducing what's referred to as an accommodation coefficient. And the accommodation coefficient in terms of a thermal energy transfer is defined as shown here, where the temperature Ts is the surface temperature of the particle, Tg is the gas temperature, and what Tf is the temperature after the molecule's been scattered off the surface. So if it comes away, obviously, as the surface temperature, then this ends up being unity, and it looks like a continuum limit. If it comes off much lower, then the accommodation coefficient is very low. And you can introduce then the accommodation coefficient into the governing equations. For example, you can introduce it into a heat transfer process in terms of a convection coefficient and look at how it's going to affect this energy transfer. But what it ends up basically saying is, if I look at a particle energy exchange, what it may mean is that, you know, now if the heat is being generated within the particle and I'm trying to conduct that heat away by the gas surrounding, it may not be able to take the energy away as fast. So typically, if I'm in the kinetic limit from a continuum point of view, I always assume the particle temperature is very similar to the gas phase temperature because I'm very efficient in transferring energy back and forth. So there's no difference in terms of the particle temperature and the fluid temperature. But now with these accommodation coefficients, if they're very low and energy is being converted and formed within the particle, that means the temperature of the particle can actually get higher than the surrounding gas because I can't exchange it that fast. Okay, that typically happens at higher pressures. If I'm at lower pressures, I don't see it as much. But people have seen it in terms of small carbon particles as well as aluminum particles. And it affects then the d squared law or the d to the 1 law. Okay, it actually, in that transition regime, the fact that I'm not able to transfer energy actually ends up affecting how the particle burns in terms of these overall relationships. What happens also as the particles get smaller, as I mentioned, if you're at low pressure and the temperature of the particles are very close to the surrounding temperatures, and that means I'm below the vaporization temperature of aluminum, then the nanoparticles are going to burn not in the vapor phase, but more like a shrinking core model. And what this means is I'm not going to be able to vaporize the metal oxide on the surface. I'm not going to be able to vaporize the aluminum. And so the question is, how does the nanoparticle oxidize? And for the nanoparticle to oxidize, what it means is I've got to have the oxygen be able to diffuse across the oxide layer, or the aluminum to diffuse outward, and either have the reaction on the outer interface or on the inner interface. Typically, at higher temperatures, the oxygen's diffusing in, and so I have what looks like this shrinking core model where the reaction occurs at this interface and I consume the process. If I go through the theoretical analysis of this shrinking core model, I can also assume then that either diffusion of the oxidizer across the oxide limits the reaction, or the surface reaction at the interface limits the reaction. And I can end up then with either a d squared type relationship for this shrinking core model or a d to the 1 relationship. So even if I don't have a vapor phase combustion, the process can be diffusion controlled in the condensed phase or reaction controlled. But what happens typically, and this shows the theoretical results for that, if it's diffusion controlled, I end up getting the R squared dependence. If it's kinetically controlled in the condensed phase, I get the R dependence. And what that typically means is if I were to look at the reaction rate as a function of the extent of reaction, what you find is if it's a diffusion controlled process, you see the reaction rate fall off very quickly. So it's actually been observed if I'm burning nanoparticles in a combustor that the nanoparticles may not burn as efficiently as a micron particle. And it's a consequence of the fact that I'm switching from this vapor phase combustion process to this shrinking core model, and it takes too long for the oxidizer to get across that oxide layer, and I never burn out then the aluminum in the inner core. Okay, there's also been other theories, and I'll just show you a couple other theories how nanoparticles have been assumed to burn. This is a theory where if I have a very high heating rate, so this might occur in a detonation. It's been proposed that, if the heating rate into the particle is very fast, the particle has a very low mass, very low heat capacity, so it's going to want to raise its temperature very quickly. And what happens then is as the energy quickly, and because the Lewis number is such that I diffuse heat faster than mass, I quickly heat the particle. And what that means then is the temperature of the particle builds up internally, and if I have this structural shell about the outside, as the particle tries to start to melt and heat, it starts to expand. And you can build up pressures that's been shown through molecular dynamics calculations as high as tens of gigapascals interior. And what that is thought to do then is basically spallate the shell and basically explode it. And what you end up seeing then are aluminum clusters that fly out, very small aluminum clusters, and that makes the burning process very quick. As I said, this has been only shown theoretically, and it would occur in very high heating rates. If you lower the heating rates, more typical of combustion, you see something like it's been done in these molecular dynamics calculations here, which have been done with billions of atoms. This is some work that was done at USC. And what you typically see here is as the aluminum particle starts to heat up, the initial reaction is between the aluminum and the aluminum oxide. You don't have diffusion across yet, so I'm reacting aluminum with Al2O3, and that creates basically another version of AlXOY. That's an exothermic process, and during that process, it starts to open up pores, and the oxygen starts diffusing in, the particle starts heating up, and when it gets up to about the vaporization temperature of the oxide, then you start seeing aluminum vaporize out of the system, more like you would expect then for a lower heating rate in aluminum in general. But there's other interesting things with nanoparticles, and you can actually find reactions that occur below the melting temperature of the aluminum. And here's an example, and similar results have been seen for O2, but I show it with CO2 as the oxidizer. These are experiments that were conducted in a thermogravimetric analyzer. So what you're seeing on the top here is the mass gain as a function of heating up particles, and also on the bottom side here is basically the energetics of the reaction. So if the peak goes upward, it's an exothermic reaction. If the peak goes downward, it's an endothermic reaction. And what you see then, this temperature right here, about 670, the endothermic reaction, that's the melting temperature of aluminum. And if I'm dealing with very small particles, say on the order of 30 to 40 nanometers, you start to see mass gain right away and heat release below the melting temperature. So this is actually a solid reaction of aluminum reacting with the oxidizer. There's no melting occurring. And so it's unusual reaction that is sort of occurring in the solid state then. As I start to increase the particle size then and get to micron sized particles, you lose basically that solid state reaction. You see the melting condition, and it's not until after the aluminum is melted that you start to see the exothermicity and the weight gain in the particle. So again, the idea of how's the energetics of this nanoparticle being affected? I mentioned as the particle gets smaller, it starts looking like the characteristics of the atoms on the surface. And because they have different stressing of the bonds, there's been theories that they can actually store more energy also in the surface atoms than the bulk. generally, what happens also with the oxide is as the particle heats up, the oxide changes to different polymorphs. So if I start off with an amorphous layer on the surface, I could start to transition as I go to higher temperatures to basically gamma aluminum and then to alpha aluminum. As I do that, the density of the oxide changes. And so as the density changes, it's going to basically open pores up and allow oxidizers to get to the surface quicker, and also allow the particle to lead to a reaction where I have the oxidizer coming right down to the aluminum surface and lead in each of these steps to a rise in temperature, eventually to the melting point of the oxide and get full ignition. Again, these are just a little bit more emphasis on the differences in nanoparticles. These are experiments where a flow reactor tube experiment was conducted, and a single particle at a time was passed through the flow reactor, and it was captured by basically a mass spectrometer with a microprobe. And one looked at basically the extent of reaction of that particle. And what you end up finding as you decrease the temperature and you look at different size particles, you can actually change the activation energy of the reaction. So again, very small particles have a lower activation energy. They're going to react faster at low temperatures. If I go to larger particles, they have a higher activation energy. They don't react faster. And this could be related to also a diffusion type rate constant as well. And if you look at and assume this is a shrinking core model, what you end up finding is these particles burnt with a characteristic time that was proportional to the radius to like the 1.6 power. So there's a combination of diffusion affecting the rate constant as well as the chemistry within the core. Okay, so let me just spend a couple slides here. I've showed you how aluminum burns by itself. What happens, again, when I add it back into a composite propellant? And I don't want to spend too much time here, but you may ask, most propellants are typically designed to be fuel-rich, right? And that's, as I told you, because I want to have a low molecular weight. And so you might ask the question, well, why do I want to add more aluminum then and make it even more fuel-rich? And the question comes about because and is answered in a couple reasons. First of all, the aluminum has a high density, so I can increase the density. Remember, it's got like 2.7, oxidizers about 2, binders about 1. So if I add aluminum, I'm going to increase the overall density. I'm also going to increase the overall energy density. And lastly, I asked the question, well, what does the aluminum react with? The aluminum is going to end up reacting not with molecular oxygen. It's going to end up reacting with CO2 and water vapor. And it's going to reduce the water vapor to hydrogen, and it's going to reduce the CO2 to CO. So it's going to end up making lower molecular weight species in the end. So overall, it's favored to add. And what you end up finding then is if you were to add it and look at a rocket motor and add, proportions in about 10 weight% or so, you end up finding that you get an increase in ISP about by 10%, and the propellant mass fraction in a motor goes up by about 15%. It also can reduce combustion instabilities, but there's negative features as well, as some of those, as I said, we talked about propellants being smoky. It's going to create slag, two-phase flow characteristics, drag within the flow, but and it could actually even lay on the nozzle and change the characteristic dimensions of the nozzle cross-sectional area. I showed you some pictures of how aluminum burns. Typically, the aluminum will rise to the surface. Its melting temperature and its ignition temperatures are typically higher than the surface temperature of propellants. And remember the size distribution. Remember, I showed you the size distribution of aluminum particles was in between the fine size and the medium size. And then I had these very large oxidizer particles. Well, what happens is the aluminum particles, when they come to the surface, start to accumulate in these pockets between the large oxidizer particles, and they basically can reside there for a period of time in this melt layer of the binder. And if they reside in the melt layer of the binder, what happens is the oxide can start cracking, aluminum can start diffusing out to cracks, and the particles start to sinter, and I form accumulates. And eventually the particle size can continue to grow until it's large enough, and it's much larger than the original particle sizes I put in, typically 20 micron. They can grow up to a few hundred micron before they come off the surface. And that's going to change the burning characteristics as well. And so what you see is basically the growth of these accumulates and aggregates and agglomerates in what looks like a pocket model. And I show the characteristics of that, you'll see here in a second. But this is basically the shuttle propellant burning. The shuttle propellant, if you remember, was P-band, was the binder, aluminum particles, and AP crystals for the oxidizer. And what I'm showing in this picture on the left, there's a dashed line right at this point right here. This is at an instant in time, this is where the surface was. And you can see then as the surface is regressing downward, I'm accumulating aluminum particles at the surface. They start growing because they're concentrated in these pockets between the large AP crystals, and their size can grow much larger than the original particles. And eventually, because of convective effects, drag effects, they're going to be dragged off the surface, and I'm going to see the aluminum particles burning above the surface. If I turn the lights on and look at one of these particles, this is what I'm going to see then. I'm going to see basically the core particle here. If you look closely, there's an oxide lobe here that's developed, and this is now the flame structure that goes around the flame. So no longer you see this nice spherical flame that I showed you earlier when we were doing the scientific experiments, but because of the convective flow, you see this tail coming off of the surface. And because of the tail, you can have recirculation behind it here, and you can accumulate then oxide on the surface, and you get this multi-size distribution of the oxide products that are related to the original particle versus what's formed in the flame zone out here. So if you put these particles then on a hot plate, just as a simple experiment, what you end up seeing to simulate what might be at the surface, here's two aluminum particles that were put on the surface and heated to like 1400 degrees C. You can start to see, due to the crack formation, the change of the polymorphs of the oxide, you can start to see aluminum flow out a little bit, and you start to see this sintering process. Okay, and this is the sintering joint here. And what ends up happening then, you start forming what looks like elongated particles joining together as just individual particles that are sintered together. And eventually you'll find then the aluminum starts to melt and engulf those primary type particles, and you get these larger particles, which are basically then your aggregates that form and eventually come off the surface. And here's a picture then of actually the original particles starting to be engulfed by molten aluminum around it. That's going to be lifted off a much larger particle. So one of the questions is, how does this process actually change the combustion process? Because no longer do I have this nice pure aluminum particle, but I got basically a particle, large particle, that's made up of a lot smaller particles. I think I've pretty much explained what's in this slide here. What you typically see is, as these particles burn, because of the coarse oxide particles, the aluminum particles start to gather in the region where the small AP particles are. They have time there to be held back in the molten layer. They build up in size, and they eventually come off as much larger particles. So you end up seeing something that looks like this then in a cartoon. The aluminum particles start to gather in the pockets between the large particles. They start to sinter. They start to form these accumulates. Eventually then they agglomerate up, which look like a large particle that comes off the surface, and then they burn above the surface. Okay. And then large enough, they still follow what may look like a modified d squared law. This kind of shows the effect of pressure on the size of those particles at the surface. If I increase the pressure, that means the burning rate's increasing. So the particles have less time to stay in that melt layer and accumulate and sinter to form big aggregates and agglomerates. And so if I increase the pressure, the burning rate goes up, and the aluminum particles coming off the surface decrease in size. So their burning time is going to be shorter. Okay, and it's also a function of the AP particle size as well that's around it. If I'm replacing the AP with very small if I'm replacing the aluminum with very small AP particles, you can also see an effect on when this transition occurs. The other thing, just to end this up then, what's of very importance because of two-phase flow characteristics, drag in the motor nozzle and the flow system that was going to change the thrust characteristics, is what's the size distribution of the final products being formed. It's also important with regards to instability characteristics in motor. And typically you'll find at least a bimodal distribution. And the large particle size of the oxide being formed, as I said, is related to the primary aluminum particle, and the smaller 2-micron size is related to the particles that are formed in a reaction zone that are first at the nanometer scale and then aggregate up to basically a few micron in size. And knowing this distribution, as I said, is very important in terms of predicting performance of motors. Factors that influence the agglomerate size mainly is really how fast the burning process occurs, whether or not I have a real high aluminum content, if I'm using burning rate suppressants to slow down the burning process, if I have forming a melt regime where the particles can stay behind, or carbonate, it's just residue where the particles can stay behind. And typically, to solve the problem, sometimes people try to modify the aluminum particles. They actually will put coatings on the surface to prevent the sintering problems so that you don't form the agglomerates. I want to come back to the nanoparticles before I just finish this one set of slides here. And if I look at an AP composite propellant burning, and it has micron particles in it, this is a simple one-dimensional flame burning. And what you see here is the aluminum particles come off the surface, and because they're large particles, the ignition temperature is higher. And it takes a little while then for the particles to ignite, and they burn further away from the surface. So depending on the heat feedback to the surface, the burning rate may not be as affected as much by the presence of large aluminum particles. If I substitute these large aluminum particles with nanoparticles, what you see, this is where the propellant surface is now, you can see the nano aluminum particles burning right near the surface. So I got a much more direct heat feedback to the surface from the combustion of the aluminum, and as a consequence of that, I accelerate the burning process. And what you can see on the right here is just a plot of the burning rate versus pressure, where some of the micron aluminum is replaced with nano aluminum, I think 50% of it, and you see an increase in the burning rate, much like you're seeing on the picture over here. But what's kind of unusual is this plot here. Remember, I actually showed this plot earlier. This was the d squared law for aluminum particles. You got something like really d to the 1.8 instead. And what you would have anticipated then, if I go to very small particles, something like d to the 1. Okay, but experimentally, this is actually what you observe. So if you remember, I said, if you put nanoparticles in and you just substitute them for micron particles, you don't get the performance you would expected. I don't get this short burning time down here. It's actually larger. This is more like d to the 0.3. So why is it d to the 0.3 versus d to the 1? Okay, and there's been a couple hypotheses why that may occur. If you look at the burning surface here of propellant with a micron particle, as I said, it sort of forms this agglomerate that comes off the surface and it starts burning as a diffusion flame. If you look at the nanoparticles, when they come out of the propellant, it looks like they've already started to sinter and form aggregates. So their overall particle size, their dimensions, is really starting to change. And if you remember, I said some of the advantages of nanoparticles and disadvantages was what happened to the sintering temperature. As I go to lower temperatures, the sintering temperature also lowers. And what this means then is I start to actually sinter the nanoparticles together, and they start to form these aggregates that start growing up, and it no longer looks like a nanoparticle. And if you theoretically look at this, you can look at it in different ways. Why n to the 0.3? Well, the particle no longer looks spherical. It has fractal dimensions. If you assume it has fractal dimensions, what you can find is that the surface area is no longer directly related to the particle, the diameter. It's related to some fractal dimension that typically somewhere between 2 and 3. So if you go back through the analytical analysis and look at how the relationship of the burning time is related to the diameter of the particle, you end up finding something like this, where the burning time is proportional to the diameter of the particle raised to the power of 3 to minus the fractal dimension. And if the fractal dimension changes somewhere between 2 and 3, then the exponent now is somewhere between 1 and 0. So it starts to look like that much lower value. So that's one possible explanation. The other possible explanation is what I just was also talking about and showed in the other plot, is the fact that I've lowered the sintering temperature. Okay, and these are some molecular dynamics calculations that Mike Zachariah did at UMD. And what you see is you can start to coalesce the particles at a lower temperature. They sinter together, and as I do that, I form these aggregates. And notice this is also changing the fractal dimension. But what I also see then is the time for this to coalesce into a spherical particle is on the same time scale as the burn time now. So if you're to go through and calculate a coalescence time, which is really composed of 2 times, a time to heat the particle and a time to fuse the particles together, what you find is these times here are typically shorter than the actual burning time. And so now the problem with burning these particles at the nanoscale is they're going to end up potentially sintering together, fusing, and I'm going to end up back with a micron particle, even though I started off with a nanoparticle. I'm going to lose some of its small characteristics. So if this actually happens here, what it means is I didn't really know the original dimension of these particles, and this would have been a much larger particle than what I'm assuming it was, and essentially it would actually move over here, and it would fit on d to the 1 curve then. Okay, so I don't know if you want to take a short break, or should we just go on? Anybody need a short break?